So we're going to consider some things that are going to affect your solubility, pressure and temperature and structure, and we're going to throw in electrolytes in here because we really need to understand electrolytes because they affect how much stuff you actually put in solution. So back to Chem 111 for a moment. We need to separate strong, weak, and non-electrolyte. Strong electrolyte simply means it makes lots of ions in solution, and this is going to be any soluble ionic compound. So this is back to your solubility rules like NaCl or potassium nitrate. If it is a soluble ionic compound, it's going to make many ions in solution. If it makes many ions in solution, it's going to conduct lots of electricity, but it's also going to affect how much stuff we put in solution. A weak electrolyte makes a few. These are weak acids and bases. So these are weak acids and bases, and we're going to cover that in the next few chapters in Chem 112. So for right now, just accept they're there. Non-electrolytes are no ions. These are compounds that are not dissociated, and these would be molecules. So for example, if you had sugar, sugar has no ions in it. We know it's not an ionic compound. It will dissolve in water, but it's not going to produce any ions. Therefore, it's a non-electrolyte. So again, what does this mean? If we have a solution of ethanol, C2H5OH, C2H5OH, C2H5OH is not ionic, therefore it is a non-electrolyte. Therefore, if we put it in solution and we try to see if it will conduct electricity, it doesn't conduct. If we have potassium chloride is soluble, meaning it dissociates 100% into potassium and chloride. Electricity is the flow of charged particles, and it's because the charged particles can move, we can conduct. Acetic acid, we're going to discover, is one of our weak acids. And when we put C2H3 O2 in water, it's going to make just a few ions, about 1 out of every 10,000. Acetic acids will dissociate and make an ion, and it will conduct a very little bit of water. Don't memorize that. So, solubility. There are lots of things that can affect solubility. We are going to consider structure effects, pressure effects, and temperature effects. For pressure, this is only going to be gases. But for temperature, we're going to look at both a solid into a liquid as well as a gas into a liquid because they have two very different responses to changes in the temperature. So, structure effects. Structure effects could look like this, where we would look at vitamins. The structure of a molecule affects its solubility. So if we think about our vitamin C here, our vitamin C has all of these OHs. All of these OHs mean if we try to put this into water, the water is going to hydrogen bond on all of these groups, and this is going to be very, very soluble. So we say that vitamin C is water soluble. This affects its metabolism. Vitamin A, on the other hand, has only one OH over here, and the rest of this entire mess is nonpolar. As the length of a nonpolar chain on a molecule grows with respect to a nonpolar piece, it becomes more and more insoluble, and vitamin A does not dissolve in water. It is, in fact, fat soluble or nonpolar solvent soluble. All right, pressure effects. Pressure affects mostly gases, and we're only going to do gases here. So let's think about taking a can of soda and opening it. If you take and you open a can of soda, we know that the gases will come off, and we know that our if we want to put gas into a soda, so let's imagine that we have a Coke here, and we want to take and we want to add carbon dioxide to our soda, we're actually going to have to put lots of carbon dioxide over here as a gas, and as we increase the amount of carbon dioxide as a gas over the Coke syrup or liquid, we're going to dissolve more and more of our carbon dioxide in that. Henry's law says that the amount of gas dissolved depends directly on how much of the gas is above the solution. So the more carbon dioxide you want in here, the more carbon dioxide you put over here. This has some very interesting effects. In 1986, there was a disaster in Cameroon at around a lake called Lake Nyos. We know some things about Lake Nyos. We know that Lake Nyos itself is about 100 feet deep, and it is over a split in the crust of the earth, and gases, volcanic gases, seep into the bottom of the lake. And we have carbon dioxide and sulfur dioxide and all sorts of stuff seeping in down here. Now, the pressure down here is very high. And because the pressure down here is high, the solubility of these gases down here is very high, and lots of gas can dissolve the bottom of this lake. What they think happened is that somehow a disaster occurred, maybe an earthquake, something that caused this carbon dioxide of this lake to become unstable, kind of like shaking a can of Coke. And this carbon dioxide came shooting out of the lake. Carbon dioxide is dense. It blanketed the land, and about 1,700 people were suffocated from the carbon dioxide. Now we have a vent in the lake where we've taken and we're just recirculating the gases here in the bottom, shoving them out the top, trying to prevent this from happening in the future. Another case of this is also fascinating. This is Caisson's disease, or the bends. And as you dive deeper as a scuba diver, the nitrogen in your blood becomes more and more soluble. And as you start to come up, the nitrogen becomes less soluble, and you actually get little bubbles of nitrogen coming out of your blood. It takes and it goes into the joints in particular, and it becomes very, very painful. We don't want that to happen. Again, it'd be like coming up and shaking a bottle of soda inside your bloodstream. We do a couple of things. We either come up very slowly and re-equilibrate, or we take the nitrogen in our air tanks and we replace it with helium because it has a smaller set of London dispersion forces, therefore it's less soluble in our bloodstream, which is mostly water. All right, the math on Henry's law. Henry's law just says the solubility depends on case of H. Case of H is Henry's law constant. This is temperature dependent. So we dig it up for a temperature as well as for a gas. And it says that the solubility depends on this constant times how much gas we have over the liquid. So for an example, how many grams of ammonia will dissolve in 0.1 liters of solution, given that that's its partial pressure? And again, we're going to be given the Henry's law as constant. This would be at some temperature, even though that temperature may not be stated here. So we have 7.6 torr. Our Henry's law's constant is in atmospheres. We know there's 1 atm for every 760 torr, giving us 0.010 atm. That is the pressure above the gas. Our solubility of our gas, our ammonia, is going to equal the pressure, 0.010 atmospheres, multiplied by the Henry's law constant, 58 molar per atm, giving us 0.58 moles of ammonia per liter. The question then is how much will dissolve in 0.1 liters? So if we take 0.1 liters, we multiply by 0.58 mole per liter, we are going to get 0.058 mole of ammonia multiplied by the molar mass, 17 grams per mole. And you're going to get a total of about 1 gram of ammonia can dissolve in about 0.1 liters of solution. Temperature effects. We think of that increasing the temperature will increase the solubility. That works for some, but not all solids, and it never works for gases. So let's look at some examples. In order to figure out the solubility, you really are going to have to go to the lab and you're going to have to graph it. If we look at sugar, we see what we know, and that is that as we increase the temperature, we're going to increase the solubility. But if we go down here and we look at our cerium sulfate, we notice that as we increase the temperature, it in fact becomes less soluble. So for most solids, increasing the temperature will help. For some, it will not. How do you find out? Go to the lab. Gases, on the other hand, are very consistent. And with gases, as the temperature of the liquid goes up, the solubility of the gas is going to go down. So all gases are less soluble as the temperature goes up. We know this, for example, because we know that if we have oxygen in water and we want our poor little fish to breathe, we cannot have this at high temperature. If we put this in really high temperature, all the oxygen will bubble out and our poor little fish will die. There is actually a name for this process, and this process is thermal pollution. Thermal pollution simply says that as the temperature of water goes up, the solubility of oxygen goes down, and therefore, if you have warm water, you're going to have little or no oxygen, and you can get massive die-outs as the oxygen bubbles off and the fish have nothing to breathe. We also see this in a very interesting case. We know that the total pressure of carbon dioxide, or the partial pressure in the atmosphere, is going up. Therefore, the solubility here of carbon dioxide in the oceans goes up. Therefore, we do have more carbon dioxide, but notice also temperature effects. So if we consider our poor little planet here, and we realize that the waters at the poles are cold, carbon dioxide, when you put it into water, makes acid, and the pH of our oceans at the poles is going down. Our water at the poles is becoming more acidic, and it's doing massive amounts of damage to the plant life and the ecosystems there because of the effects of pressure and temperature on solubility.